At the end of the last video, we were discussing that there are many different ways and methods that you can use to balance an equation. In this video, we are going to go over one of them. Let's begin. We're going to start off fairly simple, and then we'll kind of make it a little more complicated and complex. I'm a very visual person when it comes to balancing, so there's your chemical equation. I'm going to separate my reactants and products with a line. Then I'm going to take my atom inventory. I'm going to count my number of atoms. So I have 1 carbon, and I have 2 oxygens. On the other side, I have 1 carbon, and I have 1 oxygen. I'm going to put a bracket around these two because they are together. They form a compound, and that bracket helps me to remember that whatever I do to one of them, I have to also do to the other. So now let's actually begin our multiplication process. I have 1 carbon on each side, so they appear to be good. I have 2 oxygens on the reactant side and only 1 on the product side. So I multiply by 2. I multiply oxygen by 2 because of this bracket. I also have to multiply my carbon by 2. So now my oxygens match on both sides, but my carbons don't. So I go back to the other side and multiply by 2. You'll now notice that there's 2 carbons and 2 oxygens on each side. To complete this reaction, I have to add my coefficients. Whatever I multiply by is my coefficient. So I multiplied carbon by 2, so it gets a 2. I didn't multiply the oxygen by anything, so I can just leave it. It's technically times 1. And I multiplied my CO by 2, so it gets a 2 as well. Let's try the next example. You're going to start by drawing your line, and then we're going to take our atom inventory. If you'd like to try this part on your own, please pause the video now. Let's go ahead and do the atom inventory together. So we have 1 carbon and 4 H's. I have 2 oxygens. I have 1 carbon, 2 oxygens. And then over here I have 2 H's and 1 O. I like to keep my oxygens separated into the compounds that they're connected to. However, again, different methods for balancing may do this differently. Our overall goal is to get the same number of each element, same total number on each side. So right now my carbons appear to match. I'm going to go down to my H's. I have 4 over here. I only have 2 over here. So I'm going to multiply by 2 to get 4. The bracket tells me I also have to multiply oxygen by 2. So at this time my hydrogens appear to be good to go and match. So do my carbons. Now, the last step is to make sure I have the same number of oxygens on each side of the reaction. On the reactant side, currently I have 2. On the product side, I have 2 plus 2 for a total of 4. So I need 4 total oxygens on the other side as well. So I'm going to multiply by 2. And now my totals all match. I'm going to add in my coefficients. I multiplied oxygen by 2, and I multiplied water by 2. And I have completely balanced this reaction. At this time, yes, this is a more complicated problem. Please pause the video and try this last example. It is okay to have 3 elements within the same bracket, and don't forget to distribute the 2 to what's in parentheses. Please give this problem a try. Okay. The final answer is shown. I haven't shown all the work just yet. but there should be 3 FeCl2, 2 Na3PO4, 6 NaCl, and then Fe3PO4 too. I'm going to just start with iron. It really doesn't usually matter where you start, and if you get stuck, just pick a different starting point. So iron, there's 1 on this side, there's 3 on the other, so I have to multiply by 3. The bracket tells me that this also has to be multiplied by 3. I now, because I just changed Cl, I'm going to focus on that. I have 6 Cl's on the reactant side, 1 on the product, so I have to multiply by 6. Again, because of the bracket, I also have to multiply sodium by 6. So my chlorines now match. Now I've just changed sodium, so let's change it on the other side. I have to multiply by 2 because I need 6 of them. And then again, the bracket means I have to multiply the whole thing by 2. So I have 6 sodiums on each side, and now I also have the same number of P and O on each side. And then what I multiplied by becomes my coefficient. So I multiplied by 3, multiplied by 2, and multiplied by 6. This is again a skill very similar to nomenclature and the molar conversions and the other things we will be doing that needs to be practiced to become good at it. Let's continue on. This slide contains additional balancing practice problems for you to try. Okay. At this time, you should pause the video and attempt these problems. Please check your answers to these practice problems. Make a note if you did not get any of them correct, and be sure to ask your instructor for assistance. We are now going to move on and discuss different reaction types that exist. The first type of reaction that we're going to discuss is called combination or synthesis. Okay. It's defined as exactly what it says. You're ending up going from 2 things to 1, or maybe 3 things to 2. So it's when 2 elements or compounds become 1. So 2 to 1. As you can see in the examples, sometimes we have elements combining with each other to make a compound, as shown here. Or we can have 2 compounds combining to make another compound, as shown here. In addition to identifying reaction types, something you're going to need to be able to do is to predict the products. For the most part, we are going to be predicting ionic compounds, so we'll be crossing our charges when we do these. So you would know it was a synthesis or combination reaction because you'll be provided with 2 elements, and the only thing you can do with them is put them together. So Mg has a charge of +2, and nitrogen by itself in an ionic compound has a charge of -3. So I'll cross my charges, and the predicted product would be Mg3N2. Please attempt the next 2 practice problems. Don't worry about balancing, just predict the products by crossing your charges. Please pause the video now. Please check your answers. You should have gotten CaCl2 and Al2O3. Once the products are predicted, you can also then go ahead and balance. Predict the products first, and then go back and balance as necessary. The second type of reaction is decomposition. When something decomposes, it breaks down. So basically, this is defined as breaking a compound down. Usually into its 2 component elements. You're going from 1 thing to 2, or again, possibly, 2 things to 3, so on and so forth. This can be where a compound turns into two elements, or where a compound that has a polyatomic ion turns into two smaller, simpler compounds. Once again, you should be able to predict the products here. Now we're breaking down these compounds into their elements. You're going to have to remember your diatomics because sometimes elements require a 2. So if we're going to do H2O, we know that the two component pieces are H plus O. And then we have to go, okay, are these diatomic? They are. So you're going to label this actually as H2 plus O2. Once again, after you predict the products, you would balance it. Please pause the video and try the last two examples. The mercury oxide should have broken down to mercury and oxygen is diatomic. The magnesium carbonate has this polyatomic just like this did, and it would break down to MgO plus carbon dioxide. On a test, you were more likely to see examples like these than the one with the polyatomic. Let's continue our study of reaction types. The next type of reaction is a single replacement reaction. We're going to abbreviate that as SR. And again, it's exactly what it sounds like. Something is going to replace something else. So it's when one element replaces another. These reactions are usually an element plus a compound turning into another element plus a compound. Something is always single on each side of the reaction. Cations replace cations, and anions replace anions. So a metal is going to replace the metal, and a non-metal is going to replace the other non-metal. As you can see in the examples, sodium is single and all alone. It's a metal. It swoops in and replaces the potassium. And now on the other side of the reaction, potassium is by itself. In the second example, F, which is a non-metal, swoops in and replaces the non-metal and leaves Cl alone. You'll see that the F and the Cl have a 2 because they are diatomic when they're alone. Okay. H usually acts as if it's a metal. It is a cation when it's in acid form. So H is going to be a positive charge. For the predicted product examples, you would need to know that zinc has a +2 charge. That'll be helpful. Let's do the first one together. Once again, we're going to assume that these are ionic compounds. So the K is going to swoop in and replace the Al. So Al is going to be by itself. And then we're going to have to take the charge of K, which is +1, and the charge of nitrogen, which is -3, and form K3N. So remove whatever is going to be by itself, and then use your knowledge of ionic formula writing to cross your charges to predict the second product. At this time, please pause the video and try the last two examples. Please check your answers. Zinc has a +2 charge. It's going to swoop in and replace the H. H is diatomic, so it needs a 2. And then Zn +2 crosses with Cl -1 to make ZnCl2. Sodium's going to swoop in and replace the H and leave it by itself. Okay, so again, H is diatomic. And then Na is +1 and O is -2 to make Na2O. Again, at this point, once you've written the formulas, you can balance. Never try to balance first. We will continue our study in our next video.